If you keep the refrigerants leaks in check, an HFC system will have a lower carbon footprint than a CO2 system. That was a thought. Back in the day, CO2 compressors were certainly relatively inefficient. They've improved year on year, etc. But we always thought that, just stop leaking. And once you do that, your total environmental warming impact, which a lot of your listeners will be familiar with, but if they're not, that's taking your refrigerant leaks, your fugitive emissions from them, the scope 1 emissions, and adding them to the scope 2 emissions. That's your indirect electricity consumption. And in the main, there's a couple of issues that I realised more than a few years ago now that were just incorrect.
Welcome to another CO₂ Experts Live. So pumped up that each week you come back and you trust in the knowledge and the people that we bring to share knowledge from all over the planet. And if you're listening on the podcast, don't forget to share this with someone else. If you hear something that really intrigues you, reach out. We're here to help grow your knowledge. Send me an email, info@refrigerationmentor.com. We're here to grow your CO₂ knowledge and really refrigeration knowledge. We're here to uplift the industry by bringing you the experts from everywhere around the world and their different knowledge, different experiences, and different way of seeing things, because the way refrigeration is the same everywhere around. It works the same. Thermodynamics works the same, but the way we look at it could be a little bit different. So this is why getting perspective from different people and coming up with your own ideas and putting it together is so important. This is how we make the industry better. This is how we transition and we move forward. And I'm super excited today. I've heard lots of great things about Conor, the stuff that he's done in the industry over the last couple decades, and consistently continues to try to push the boundaries of his thoughts and his learnings. And we're going to be diving into this transition from really HFC into CO₂ or natural refrigerant, because this is important. There is a massive shift happening around the world, and different people have different opinions. If it doesn't leak, if it leaks, if we use this, we use that, and naturals, yes, naturals, no. And everyone has their own opinions, but it all comes back down to data, you know what I mean? And how we share that knowledge together, because collectively we got to work together to make our industry better. That's why we're always trying to uplift it. So super excited about this conversation with Conor, because he has so much knowledge and experience in thermodynamics and all the engineering he's done over the past 20 years. Conor, welcome to CO₂ Experts. How you doing, brother?
Well, I don't know how to follow that introduction there, Trevor. No, it's good to be here. Good to be here, and hopefully, I might be able to share something. Obviously, you had so many experts on currently, so hopefully, I'll be able to add something new, or a slightly different perspective. Hopefully not too much of a zealot, maybe, but either way.
No, this is it. This is what the conversations are about. We need to have more of these conversations, right? Because you have a ton of experience in thermodynamics. This is what your background is, where some listeners have more technical background, some have more sales background, but at the end of the day, we're all in refrigeration trying to work towards a progressive industry. So I appreciate you taking the time to do this.
So yeah, when we discuss this, we were going to look at like the three things of what we learned about when certainly the UK was starting its transition to transcritical CO₂. So I was at a plant manufacturer who sadly now passed about 20 years ago now. Jesus, which made effectively HFC compressors.
Feel old. Make us feel
I know. It's that meme of a Sega Mega Drive is no longer a 19-year-old console. That's a PlayStation 3. It's like, oh my god, that is too old. But yeah, so that's where I started with HFCs, with R448, designing plant and selling plant for to various UK end users, and the company made HFC compressors. And when CO₂ was coming onto the scene, well, we didn't really have an offering for transcritical anyway. But so we did a lot of things about modeling, etc. All in the best faith, all with the best information. But well, frankly, some of the assumptions that we made or in our models were just wrong. I think. And so that's where we'll go with, like, what was the first thing I was wrong about? If you keep the refrigerants leaks in check, an HFC system will have a lower carbon footprint than a CO₂ system. And yeah, I mean, that was a thought. Back in the day, CO₂ compressors were certainly relatively inefficient, but they've improved year on year,
Yeah.
and etc. But we always thought that, just stop leaking, and once you do that, your total environmental warming impact, which a lot of your listeners will be familiar with, but if they're not, that's taking your refrigerant leaks, your fugitive emissions from them, the scope 1 emissions, and adding them to the scope 2 emissions. That's your indirect electricity consumption. And in the main, there's a couple of issues that I realised more than a few years ago now that were just incorrect. So
Okay, I like to talk about that, because this is still a thought in a lot of people that I've talked to. They're like, if we just keep the refrigerant in these HFC systems, they're going to have a way less carbon footprint across them. And there's still a lot of people I talk to like that. All we have to do, Trevor, for these newer refrigerants, just keep it in the system.
I don't want to be a pessimist. I like to think I'm a realist, or pragmatist. And let's say you do keep it all in the system, you're still going to have the risk of catastrophic leaks. You're still going to have the risk of, let's say, the risk of service losses, of disposal losses, and all the upstream losses. I mean, if anybody's checked, Kimura's sustainability report for last year, their scope 1 emissions, and just from the processes, let alone the fugitive emissions, were I'm quoted from memory now, but in the millions of tons. I mean, it's the size of a small country, and it's all that. But I think, frankly, you cannot. In my opinion, I will get into this later. In my opinion, you've got to go with the average. You've got to go with what does the actual big picture look like, and short of frankly a massive step change. And we're you're just not going to be able to get particularly a 5% annual leakage rate on average. So, just looking at this slide, this was a part of the presentation I gave to the IOR, 3 years ago now, just regarding what was a certain view, back in 2010, and it looked like this. Effectively, you had ER404A, and the 404A wasn't frankly got a bit of a bad rap. It's a great refrigerant. It's low. It's got low discharge temperature. It's got high volumetric capacity. It's got NAFL glide. It's great. The only problem is, and it's non-flammable and it's non-toxic. The only problem is it's based on R43A, which and R125, which is incredibly global warming. And so I say the company I worked for, sort of was spearheading the movement towards the R407Fs and A's. Well, A's really, and then F came later. And you could chop your direct emissions, your leakage emissions, in half, and that was seen to be a good thing. And if you could do that, and if you could keep it in the system, you would beat CO₂ hands down. Even though CO₂ had no scope 1 emissions, it was still quite energy intensive at the time. And
I'm still hearing that. I'm still hearing that. I still hear that, and I hear like, well, there's no such thing as apples to apples comparison. On these white papers, there's always electronics and the CO₂ versus the 404, the HFOs, and there's always there's never an apples to apples comparison. I hear this.
I'll say I'd agree with that. It's actually a struggle, very much a struggle, to get an apples to apples comparison, especially now that I believe it's like in America they've got the SNAP items, which now brings in charge limited systems for certain GWPs. Same over in the UK and Europe. It's like how do you now compare a centralized system realistically with a decentralized system? Both are going to operate significantly different at part load. Whilst none of them I would say would be inefficient, a centralized refrigeration system should offer efficiency savings that aren't easily modeled. Certainly not to the unless you're dynamically modeling it, and also putting an awful lot of time into your diversity profiles. And once you get to that point, it's like, well, is the level of precision I'm going to get out of this going to be worth the time I put into it? And it's so it is a struggle. A lot of things I see aren't necessarily like for like, but it's a case of taking it down to base principles, taking what you know, and making the best educated assessment you can, really. Yep. So, but so this was like my view in 2010. If you manage leaks with 5% ALR, annual leakage rate, you're better than transcritical CO2. But leakage rates are generally underestimated. Oh. So the BRA, the British Refrigeration Association's CHUI best guide to calculating CHUI, which is a great guide, incidentally. It's got a lot in it. Gives you the sectorial factors for new systems to best practice standards, and for commercial DX, it gives you a 5% annual leakage rate.
Yeah,
which
it's not impossible.
Well, I don't know about you, Trevor, but that's
it's not impossible, but it's not happening.
It's not happening, and I think to get those, you're going to have to go to almost a very decentralized system as well. In some respects, very close coupled, very very simple. And
less
it's
hands-on.
It's
field piping. That's it. Less field, because we see our fridges in our houses. Small commercial, they leak way less than anything that is put together.
Yes, indeed.
Just more welds, more brazes, things like that.
And the other point was that and granted, at the time it wasn't really measured, but the probability, there was no stated probability factor for catastrophic failure. And it's like, well, we need to actually include that, because certainly if you're looking at an estate management where you've got, let's say you got 1,500 stalls, you could have 1,500 systems or more.
Yep.
1% leakage rate is 1% catastrophic failure is 15 stalls go pop every year. And you've got to factor that in,
yeah, for sure.
Yeah, and if you don't, then you're not gonna get there. So actual leakage rates are range from 10 to 30%. You can get some better, but again, in my opinion, you've got to take the average. It's all very well. If you've got one system, you've got a dedicated on-site engineer. Yeah, maybe you can achieve that. But who's paying for that? Who wants to pay for that?
Yeah,
it's and this is the thing. In just going by the EPA's item, they've got today annual leakage rates of 25%. It's just quite a lot. And obviously there was a Commerce post yesterday saying that some transcritical CO2 systems have apparently 100% annual leakage rate every year. But even if that's the case, it's like we're not even talking fractions. We are talking decimal places of the direct carbon footprint from fugitive emissions. It's regardless of what you choose. So that's the first point. Leakage rates back in 2010 were generally underestimated, and it took a company called to my mind anyway, an advocacy group called the EIA, the Environmental Investigation Agency, to actually go through a lot of the end users and just ask them, and then pillory them about their leakage rates. And so some end users got down to about, I think, 11% on average, and it's like, that's double the best practice.
Yeah.
And leakage
and that is the average. Some are going to be 40 or 50. Some are going to be maybe 6 or 11 is probably low. Well, no, if it's average.
Yeah. Well, if you've got 1% of your stores going pop every year, which I think is relatively conservative, then yeah. I mean,
yeah. And this is something that we've known for decades. It's not new. Like even when 20 years ago when I was in, we had leaks and we a valve opened by accident and someone didn't pipe that in a reno, and all of a sudden you lose a big charge out of a system. And this happens. Mistakes do happen. So it's not always that it's running. It could be on maintenance. I see Jeremy in the chat is preventative maintenance. You know, maybe they don't have people in that area that can even work on those types of equipment. You know, there's a lot of factors in there, but we all know that leak rates are higher than everybody talks about.
Yes, it's all very well saying. It's saying that we'll get leakage lower, and but can you get it low enough? Yeah. You need to get into low single figures at best.
And we're not saying that CO2 is leaking any better. It's bad, all of it. We don't want any refrigerants, natural or HFC. We don't want any of them to leak. So that's the whole purpose of it. We should have we want no leakage on any type of refrigerants.
Yeah, indeed. And then the next point that I was wrong about was we generally overestimated the loads. So our Chewy calculations, or certainly mine, I will say mine, I'll own it. They were based on basically peak day loads, peak day duties. You know, you're assuming you've got your cold store in a 25-degree ambient all day, which it's, you know, certainly in the UK, it's not. You're assuming that you're always at climate class 3 on your refrigerated display cases. That's a 25 C ambient and a 60% relative humidity. In the store, it's barely what we call class 0, and that's 20 degrees C and a 50% relative humidity. You've got night blinds. You're not trading every single hour of the day, and your lighting's not on for half the day. And at that point, it's like, well, if your duty's lower than you expected, then your indirect electricity is going to be consumption is going to be lower. So just a quick trace from somewhere I took today, from a chiller room, an evaporator. It's like, that's how much the valve is opening, and for frankly, most of the day that valve is closed. You know, and it's like, it's just yeah. And that's the other thing. We've not really considered that when you commissioned it, has it been commissioned so it's achieving its performance goals? As in, is it keeping the produce as cold as you said you would do? And if you are, great. And if you're not, to do so is potentially going to cost a bit more energy. So again, it's like it's overestimating that load and underestimating the leaks. So just taking that previous assumption, this is what it looks like here. This is with a 5% leakage rate, full peak loads across an annual. Well, this is a 12-year lifespan, and we're looking at 8,000 tons of CO2e over the course of 12-year lifespan, and let's say 7,000 for CO2 and a bit shy under there. But let's take the average leakage rate that the EPA say of 25%. All of a sudden, we're up at 14,000 tons for an R404A system, 10,000 for R407A, and slightly less for R407F. Yeah, if you keep it in the system, it would be nominally better, but it's not. But let's also then just let's just assume, and I say let's take the safe assumption, that we're just operating at 75% of our typical annual load. And it's like, well, in which case, there is no difference between R47F and R744. Yeah. They are, there's virtually no difference. But there was another thing which I hadn't considered at the point, is I hadn't looked forward. So I was doing all this thing for my boss in 2010, and I hadn't looked forward as to what's going to happen in the next 10 years or 15 years. And this is what happened. That's the carbon intensity of the UK national grid from 2002 to 2024. And effectively, over the last 10 years, the carbon intensity is reduced by 60%. That's all due to coal being eliminated out of the system.
Yep.
And a much wider, a much greater percentage of renewables and low carbon, low to zero carbon generation coming in. So if your energy consumption, if your energy cost is less carbon intense, then your scope 2 emissions are going to be less. It didn't necessarily matter what you did at that point. You could have done nothing over that 10 years and you would still be at, let's say a third to a half of your typical carbon footprint. Anybody, regardless of what they did. And that's what makes this look like. So our typical assumption, and if we assume in 2030, where in the UK, that is, they're looking to get to 20 grams of CO2 per kilowatt hour. This is what the carbon footprints look like for CO2. Everything else is dominated by its annual leakage rate. And that's 10%. So again, 1% better than the 11% previously stated on the range. That's a lot of carbon, and that's before we even factor in scope 3 emissions. And scope 3 and scope 3 and scope 1 will just be of much more importance over the next 10 years. Certainly in the UK and Europe than scope 2. Energy consumption will still be important. It's still going to cost money.
Yeah.
But if you're looking at it from environmental perspective, a carbon footprint perspective, net zero, how do you justify not going to CO2?
Yeah.
And
I was having a conversation with my friend Ian Toon out of Australia there last week or 2 weeks ago, and we were having a conversation of what's going on in Australia with CO2, and lots of people are like, well, it's way cheaper to run 404 than CO2. It's always hot here in Australia. And he's been doing CO2 there for over a decade. And he's like, we thought, and theoretically it shows that for our 404A or these HFCs would be less expensive in all the data, in the compressor data, the modeling, not counting the leakage rate, just the energy side of it. And he said, we've seen not the opposite, but we've seen that we were wrong. All these theoretical data saying that CO2 is going to be way more expensive and stay way more expensive. We were wrong, because we're looking at the price, measuring the cost of it, and we were way off. It's a lot lower to run CO2 than we thought. And this is evolving, though.
Yeah, well, that's I say interesting. I'd say I don't know too much about Australia, but one of my biggest things is currently for certainly for distribution centers is linking or dovetailing. Get it? Synergy, I think, is the overused term of solar PV to CO2. If you parlay any savings from CO2 capital expenditure and operational expenditure into solar PV, any inefficiency you have during the summer turns into a net benefit, as it were, because you don't have that efficiency out. You have free you have low cost, low carbon energy to basically offset anything that you wouldn't do. And that's one of the things that I look at when looking at, say, comparisons between ammonia and CO2, because that cost saving you can save on capital expenditures, you put it towards low carbon energy generation, and you are getting a better payback. You're getting lower carbon, and it's one of those things.
Interesting.
Really.
It's interesting.
Yeah. So,
and thank you for being honest about what you thought then, and how you admit that you didn't see it the way you see it today. Right. And that's from data and learning and growing and understanding of what you're looking at, because we are still evolving. This is what everyone needs to understand, is this is not the final straw. CO2 is not the end be all. At some point, we may not be needing any refrigerants at all for refrigeration. Who knows? You know what I mean? Where we're at. But right now, we are evolving.
Yes, indeed. I say it's yeah. I mean, I do hold my hands up and say there will be niches for F gases. There will be niches for F gases, but I struggle to find where they are for food retail. Frankly, yeah, yeah. I struggle.
Yeah.
And then I say, just discussing the most important thing about heat recovery, because but just bear in mind that I try to bear in mind that again, as people learn, and so whilst this might be common knowledge in the UK, etc., and Europe, it's going to be less common knowledge where transcritical CO2 isn't much of a isn't that has that much market penetration. But the most important thing to know about heat recovery for CO2 is that for transcritical CO2, it works so much better with a low fluid return temperature. Because here, if we see, we got let's say we have any sort of fluid return temperature of say 40 degrees C, which is what we were originally having during our first transition. We had heat basically an entire refrigeration heating system heating our client stores, which ran off a 46 flow and 40 degree return to underfloor heating and to cassettes, and it worked okay. And for our first tranche of CO2 stores, we just adopted the same process. But as you can see here, as it were, we've got a flash gas proportion. If we bypass the gas cool at that point of say 60%, it's efficient if you can do refrigeration and heat recovery at the same time. But it could be more efficient. And as soon as you get your mechanical engineer or the mechanical building service engineer to design their heating emitters to allow a low fluid return temperature, you see we basically increase our heating work available by 25 to a third, and we reduce our work input to get further up there. That is the peak. That is the thing that I think anybody should take away from this is effectively, sweat the heating emitter sizes. Don't, because the amount of money you'll save is just it's a lot, and it's something that's we anybody should do, because you do get a bit handicapped just regarding.
Okay, so this is good. Why don't we elaborate on that a little bit? Because you're involved in a lot of this. How can we get it to that lower fluid return? Because I've had these conversations. Well, the water comes out of the ground at this temperature, for heat pumps, because I'm dealing with a lot of heat pumps. It's way higher here. I can't get the return or fluid down there. What are some strategies that you work with people on trying to accomplish this?
So I think the main thing I look at is it's heat recovery. It's heat recovery, and that means it's basically it's free. It's free. It's not a heat pump, and yes, it's not necessarily free. Frankly, it's not necessarily free, but it's nigh on free. So let's say we've got our. Can I draw this here? Let's say in our normal
winter's day
normal sort
right
here. With normal day, that's where we go, and we inject all that heat to atmosphere, and then for that little, and this is what I basically retell everybody is if for that extra bit of work, you get all that, and that COPH is, in some cases, approach in the high double figures, and in the worst cases, it's in the high It's in the high single figures, and I'd like to see any heat pump, any what's the term? Any dedicated heat pump, ground source. Obviously there'll be some water source heat pumps that can do that. That can do that as cheaply and as more carbon efficiently than that. And that's what we need to basically get through to the clients. It's we don't want to be chucking this out. Sorry, bear a second. Where I've lost my cursor. We don't want to be chucking this out to atmosphere. We want to be chucking it into store.
Yeah. So here in Canada, even 20 years ago, when I was doing, we were using heat recovery. Like it's not something new here. But it's different with CO2 versus the 404 we were using. Do you want to talk a little bit about the differences when we did heat recovery for a 404 system now with newer CO2 systems?
So, I mean, the main difference is that CO2, not only can it control its head pressure, off the HPV, but it also has a much easier time of generating higher temperatures, a much easier time, because obviously here we're not having a relatively low temperature difference between our fluid temperatures and our CO2 temperatures. So that means not only can we have a much smaller DC preheater in this case, gas cooler. It just gives you a much easier time. So, for example, we'd be condensing up on the units we were using, up at, so that was a thing actually. But nominally we should have been condensing up at say 48 degrees to 50 degrees, which kind of, if we look at that on any compression selection software, our supposedly great COP on HFCs starts dropping down like a roof, just to ensure that we've got enough sufficient heating for the store, to get that grade of heating up. But for CO2, again, we just go to 75, 80, 85, no higher, provided we can get the heating return fluid temperature, to 30 degrees or lower, and that's not been a problem that I've ever seen. It's not been a problem I've ever seen. Once we do that, it's just more efficient in heat recovery, and it costs less. You have a much smaller heat recovery plate.
Yeah.
In comparison, it's
So one of the things is, though, we get our most heat in the middle of the summer too. This is what I hear. You know what I mean? Well, it generates all the heat in the summer, but in the middle of the winter, there's no heat generating. Our loads are low. It's really cold outside. Like today is 30 Fahrenheit or zero, like just below 0 Celsius, -1. And we're like, well, we're not generating any heat. Now you have to turn on compressors and push that up into transcritical to generate that heat. Doesn't that cost money?
Well, in some ways, yes. But first things first, we've done a bit of a step change in our work with our client. Previously, again, this combined refrigeration heating system, that concept that went from HFC to CO2 had a false load on the or just above the gas cooler.
Yep.
We'll just blow it for it. But what happened was, when we needed additional load to overcome the structural heating load and the infiltration load, we'd bring on that false load, which would bring on compressors, and which would give us the heat to overcome basically the load of the negative heat load of the cabinets and the structural loads. And it wasn't, as a heat pump in heat pump operation, it wasn't the most efficient way of doing things. It was very cost effective because we're still using the same compressors. We don't need to buy any more compressors. We don't need to buy. Yes, we have to buy a false load evaporator, which you can incorporate into a gas cooler. But you don't have to position. You don't have to take up any more space, and it's basically enables you to have a much higher utilization of existing assets, and that really works well. But when you start putting doors onto cabinets, then it's at that point when you've got to consider that having a heat pump function, an air source heat pump function on your refrigeration system starts becoming less of, oh, it's a little bit of efficiency, but it's good enough to, instead of having an efficient refrigeration pack that does a bit of heat air source heat pumping relatively inefficiently, once you put doors onto cabinets, you have if you don't change it, you have a refrigeration pack, you have a heat pump, an inefficient heat pump that does a bit of refrigeration efficiently, if I made sense, because the false load requires so much more duty to heat the store than the heat recovery can give. So what we made the decision about 4 years ago now was to take off the air source heat pump mode off the combined heating systems. So we just have refrigeration heat recovery. And whilst a lot of mechanical engineers, mechanical building services engineers will go, oh, well, that's not a lot. You're not giving me a lot. The thing that they forget, and I've not seen them really include, is the fact is whatever we're taking out in the refrigeration, we're putting in. And the refrigeration is we're still taking out 30 kilowatts of refrigeration out to the sales floor. It can only come from the sales floor. Yeah. And do they want to? Yeah. And so we're putting that back in, and plus the power input, and that is still much more efficient than just getting an air source heat pump to just chucking that energy away and just getting an air source heat pump. Yeah, and that's the thing. It's both cheaper to recover heat from a transcritical CO2 system, and it's than pretty much anything else. You will still need, certainly with doors, in my opinion, what I term auxiliary or supplementary air source heat pumps to overcome the structural loads. But structural infiltration loads, which in the UK are relatively significant on these stores. I can't speak for Canada, obviously, but yeah, at such a point, it's such an easy win for CO2 to have a heat recovery plate if you've got air source or water source heat pumps. Yeah, it's such an easy win.
No, I agree.
Yeah. So, but yeah, so.
That's amazing, because I do have these conversations with for years, and even with technicians. Oh, well, the heat recovery's off, or the heat reclaim's turned off by the customer because they say they don't get they're paying too much for the heat recovery, so it's better just to use natural gas heat or electric heat. It's cheaper. But at the end of the day, if you can reuse any heat inside the system, and this is where we're evolving too. I've been at a store where they do low temp, medium temp, high temp air conditioning and heating, all with a CO2 plant. And I'm seeing more and more of these now. And I think it's just the change. It's different, and it's still hard for people to understand that actually you have one plant that does everything versus having 40 packs on the roof, like the RTUs on the roof. It just has to be designed differently and staged differently and looked at differently. And it's not always going to be one size fits all, because that's what people are looking for. I just want this one thing that does it. No, there's different buildings, different location, different ambience, and different conditions.
Yeah, indeed. So awesome. Yeah, there is no one size fits all. But I think there is a one size fits most. I think I don't know. And then as I put on the pitch, why is carbon dioxide the future? And for me, it's relatively simple. It is the only non-toxic, non-flammable, sub 150 GWP refrigerant. That's almost enough. That is a waste product. And such is cheap and has relatively low embodied carbon. And as such, it's the only one then that be used in large centralized refrigeration systems, either as direct expansion, either as pump volatile.
Yeah.
And as I put up the hierarchy of controls here, CO2 sits here. Is it toxic? Yeah. No, yeah. Toxicity, eliminated. Flammability, eliminated. It doesn't really matter if it's an A2L, it needs to be treated as flammable. And also what happens during during combustion. So ammonia, A2Ls, especially when we consider their environmental costs, we need to consider them down here. So at this point, what's the only one that eliminates all those concerns? And that for me is CO2, and that's why fundamentally I think it's the future. It's the only one that's going to have the lowest Scope 3 emissions, in my opinion. It's the only one that's going to have the lowest. That's the other thing, is considering these over the GWPs of the CO2 alternatives. Even if they're sub 150, what do they look like over a 20-year time horizon? Because they're all they all have R32 in. And R32, is what, 677 at current AR6 values. But on a 20-year scale, it's up at, I think, 2000. And where's the next? What are the most important current times? It's the next 20 years. We don't have that long to meet. To 2050, certainly don't have that long to meet. Well, let's say 2 degrees of warming before we potentially hit some pivot points or some thresholds, and that's fundamentally why I'm such a CO2 zealot at the moment, because it just ticks all the boxes.
No, and that's fair. And there's going to be lots of you that are listening that agree or disagree, and it doesn't matter. It's just you need to understand what's going on. So, and you're coming here, listen to the experts from all around the world. And there's lots of different opinions out there, and I hear both sides of it. I'm hearing from why we should be using the CO2, why we shouldn't be using CO2 or naturals, why we should be using A2Ls versus why we shouldn't be using A2Ls and HFC. I hear all these stories from so many different people. And there's, people you can make it sound like one's better than the other. At the end of the day, none of these are good for the planet, like leaking. Like one of the things that people are like, what I like about CO2, I can just blow it off and then work on it. No, you don't want to do that. There's still POE oil in there that you're shooting out. You don't want to do it. Same with A2Ls. There's different reasons for all these different refrigerants. And if you're pro or con to it, to me, it doesn't matter. I just want you to be able to make a true judgment for yourself. Kind of like Conor did over the last 12 years. He thought he believed one way or thought one way. And over time, he's learned more and more, where he's now to the point where he sees CO2 as the future. And this is for now, because we don't know what's going to happen in the next 20 years. Maybe there's some other development that comes out that makes it more efficient, better for the planet. We don't know. You know what I mean? At this point, we don't know what lies ahead. But what I do know is that it's exciting times for the refrigeration industry, and you should get involved in the refrigeration industry, and you should talk to people that you know about why refrigeration is amazing. And we should be getting in here to learn more about CO2, to learn more about how refrigeration is changing and evolving the world. I had a conversation the other day, Conor, with someone where they were telling me, refrigeration, like food refrigeration, is kind of big. But you know what's bigger refrigeration today is data centers. You know what I mean? Like this is 25 years ago, data centers, there were data centers, but it's not like it is today, the amount of heat output that they use. So we got to be thinking and expanding our mind. And I'm heavily in supermarket, big time, commercial refrigeration, but I'm starting to expand my mind to see where do we really need the most refrigeration? It's critical for us. Food preservation, medicine, so important. But there's the other side of our refrigeration industry that's growing way faster than ever before. And we're going to see CO2 in a lot of those locations. I'm talking about CO2 way more in air conditioning, way more in data centers than I ever did before. So you'll see more of that to come. Conor, I want to thank you for taking the time to chat with us and share some of your knowledge, and because I know this is just the beginning. And I'm definitely, we're going to have many more good conversations. But what are some final thoughts for anybody listening on the podcast or watching the YouTube video? What are a couple of final thoughts?
Well, I think the final thought is look forward. don't look behind. You gotta look forward to where you're going to be, or where you want to be, because like I said, if you don't consider if you don't consider where the grid is going, and decarbonising, it's like, well, that basically rendered a whole lot of investment decisions rather moot if they were to get the most environmentally responsible choice. I say, and that's the thing. And as you know, there's very few things that are environmentally friendly. We need to be responsible, and choose the lesser of two evils, effectively. And frankly, I think the most important thing is that CO2 is big, and it's a very good refrigerant that can be used for an awful lot of things.
Yeah.
And it's probably the best one out. It's probably, for the majority of applications, the best one out there.
And I agree with you. I see more and more studies. So I really enjoyed this conversation. I've learned a lot. And if you took anything away from this, share this with someone. If you learn one or two things, because it's going to be different around the world, wherever you're at. And we didn't get into centralized, decentralized system. We didn't get into 45-degree ambience or 20-degree ambient. You know what I mean? You can dive deeper in all this stuff, and you're going to have to model it. You're going to have it designed. You're going to have it installed. The total life cycle of a piece of equipment is not just a piece of equipment. Who is servicing? Who is maintenance? Is the customers paying for maintenance? Because this is I seen a thing in the chat where they say, well, my good friend Andrew Freeberg, he says customers will dictate maintenance. You know what I mean? So even though it's needed to be more efficient and effective and save them piles of money down the road, because I've seen it time and time again. Oh, we'll just wait until it breaks, and when it breaks, we'll just pay the service guy because we don't want to pay them that maintenance. And that costs them more money in the long run, hands down. Every time I've seen it, I've seen the numbers. A lot of them are scared to show and admit how much it costs them because they made a mistake on not keeping up with maintenances, because that cost, it does cost. It costs time and money to keep a good running system. And there's a lot of other good points. I love Jim too. Also, heat recovery is key reason for our large chiller customers going with CO2 based systems. And I appreciate that. Pro chillers, they got their Pro Green system out there, but they're seeing that heat, the value of it. I remember being in a conversation with them where they've reduced tens of thousands of pounds of propane, and it's already done. The heat is done for the wash bay because of the CO2 system. Nothing else added. So there's not pulling more stuff out of the planet, not reusing other fuels to heat up the stuff. It's all done in one system. So if you think about it and you design it properly, it's going to make a big difference. If you like this podcast, please share it, like it, comment. And super excited that you're here to listen to us today. Conor, thank you so much for taking the time.
Oh, thank you for having me.
Super awesome. I see there's quite a few more questions in there. I will reach out to some of you, get those answers to you. Conor, thank you so much. And we look forward to seeing everyone at the next CO₂ Experts Live. Thank you, everyone.